Good day, students. The topic of our today's lecture is radiation hygiene. Radiation hygiene, we can belong to occupational hygiene. It may be as part of occupational hygiene, and radiation hygiene we discuss as separate section of hygiene. Radiation hygiene is an independent preventive medical science that studies the conditions, types, and consequences of exposure to sources of ionizing radiation on the body and develops radiation safety and environmental protection measures aimed at protecting human health. Radiation hygiene is divided into radiation occupational hygiene, which studies working conditions and develops radiation protection measures when working at enterprises and institutions, including medical ones, with sources of ionizing radiation, as well as communal radiation hygiene, which considers all issues of radiation safety of the population. All living and non-living on the Earth is exposed cosmic radiation and natural radionuclides from the Earth's crust, rock, soil, water, air, food, and inside themselves. Natural radiation background being composed during millions of years is added by radiation occurring due to human activity. The last one is provided artificially. Sources of ionizing radiation for scientific, industrial, medical, military, and consumptive purposes. Rapid development of nuclear energy production, or due to anthropogenic destroyment of the Earth's crust. The experience of eliminating accidents and nuclear power plants suggests that doctors of any specialties should know the basics of radiation hygiene, since they can significantly affect the consequences of emergency situations. And now we should discuss some definitions of radiation hygiene. First of all, what is ionizing radiation? It's any radiation, with the exception of visible light and ultraviolet radiation, the interaction of which with the environment leads to its ionization, i.e. to the formation of ions of both signs. Radiation safety of the population, the state of protection of present and future generations of people from the harmful effects of their health by ionizing radiation. Radiation hygiene, a branch of hygiene that studies the effect of ionizing radiation on human health and develops measures to reduce its adverse effects. And we continue discussion about some main basic concepts of radiation hygiene. And now radioactivity. Radioactivity, spontaneous transformation of elements nuclei to others, accompanying with emission of ionizing radiation. Types of ionizing radiation are wavy electromagnetic waves, here X-rays and gamma rays, and corpuscular or particles, alpha particles, beta particles, neutrons. Substances containing radioactive nucleus are named radioactive. The decay of atomic nuclei leads to a change in their atomic number or mass number. A change in the atomic number leads to the transformation of one chemical element into another. When only the mass number changes, the isotopes of this element are converted. Example, isotopes carbon-12 and carbon-14. A substance natural radioactivity is due to certain radionuclide content in the soil. Uranium 238, radium 228, thorium 232, carbon 14, potassium 40, radon 222. Artificial radioactivity arises from the decay of natural radionuclides. The main artificial radionuclides are strontium-90, cesium-137, iodine-131, and others. Almost all artificial radioactive isotopes belong to beta or beta and gamma emitters, but natural radionuclides are alpha emitters. The most potentially dangerous fragments are strontium-90 and cesium-137 because of their active participation in the biological cycle and long period of half-life. An alpha particle is the nucleus of a helium atom. Its atomic mass is 4 units. The charge is +2. With a relatively large size and large charge, the particle has a high energy. It is characterized by a large linear energy transfer and a significant linear ionization density. On this table, you can see different types of radiation, and the most important features of these types: penetrating ability in tissues, ionizing capability, and protective materials. Alpha particles are retained by the epidermis without reaching the deep layers of the epithelium. An ordinary sheet of paper is an absolute screen for them. Therefore, the external influence of alpha radiation on a person is practically safe. However, the intake of alpha particles into the body, for example with food and especially with air in the form of radon, is extremely dangerous, since the risk of a carcinogenic effect is significantly increased. Under such conditions, alpha particles easily penetrate through mucous membranes and create a high ionization density inside tissues and organs, which is the reason for the pronounced pathogenic effect. Beta particles. Beta particles also have small penetrative ability and very low ionizing ability, because alpha particles with high ionizing ability, 6,000 pairs of ions in 1 millimeter cube of tissue or air. Beta particles only 6 pairs of ions. Electronic beta decay is a characteristic of the transformations of natural and artificial radionuclides. With this decay scheme, beta radiation is a stream of electrons. Electronic beta decay occurs when the instability in the nucleus is caused by the excess of the number of neutrons over the number of protons. In this case, an electron appears in the nucleus and one of the neutrons turns into a proton. An electron is ejected from the nucleus. The charge of the nucleus increases by 1 and the mass number remains unchanged. Beta particles have different energies. Therefore, when protecting from external effects of beta radiation, a screen that absorbs beta particles with maximum energy should be used. Screens are used from lightweight materials with a low atomic number, such as glass, polymer materials, aluminum. In the manufacture of screens from heavy metals, beta particles will generate additional X-rays from which protection is also required. Neutrons have high penetrative ability, up to 10 meters, and average ionizing ability, 400 pairs of ions in 1 millimeter cube of air. And protective materials, here maybe paraffin, polymeric materials. The specific density of ionization for gamma quanta is minimal. There is no charge and mass. Therefore, their path length is rather long and can reach several hundred meters in air. By more often up to 10 meters. Biological tissues are practically not screens. Therefore, gamma radiation is a very dangerous source of external radiation for humans. In this regard, screens for shielding against gamma radiation should be made of materials with a high density, with a large number of nuclei and large electron shells of atoms. For example, such materials may be lead, concrete, and for X-rays, same conditions. Very low ionizing ability, very high penetrative ability, and protective materials are the same. Our next question will be natural background of ionizing radiation. Radiation background is ionizing radiation from natural sources of space and terrestrial origin, as well as from artificial radionuclides dispersed in the biosphere as a result of human activity. Radiative background affects the entire population of the globe, having a relatively constant level. Natural radiative background, technologically modified natural radiative background, and artificial radiative background due to the radioactivity of the products of a nuclear explosion are distinguished. Natural radiation background is ionizing radiation acting on a person on the Earth's surface from natural sources of cosmic and terrestrial origin, and is often identified with the concept of the radiative background. A technologically modified natural radiative background is ionizing radiation from natural sources that have undergone certain changes as a result of human activities. For example, radiation from natural radionuclides entering the biosphere together with minerals extracted from the Earth's interior as a result of combustion products entering the environment, organic fuel, radiation in rooms built from materials containing natural radionuclides. With the beginning of the widespread testing of nuclear weapons, global pollution of the biosphere with artificial radionuclides arose. Added to this are local, regional, and global pollution caused by waste from nuclear power plants and the use of sources of ionizing radiation for scientific purposes in medicine and in the national economy. Significant environmental pollution can occur as a result of accidents at nuclear power plants. And on this slide you can see content of natural radiative background, the main sources cosmic radiation, which give up to 40% of all irradiation, and objects of environment, soil, air, water, and foodstuffs. The radiation caused by artificial radionuclides scattered in the biosphere is an artificial background radiation, which adds only 1-3% to the natural radiative background as a whole. The radiative background measure is the absorbed dose rate. The radiative background level of the globe is 0.1, 0.5 microsievert per hour, or in other unit, 10 to 50 microRentgen per hour. In the Crimea, this level 10 to 20 microRentgen per hour. In Russia as whole, this level approximately 20 microRentgen per hour. Natural background radiation is the main component of radiative background. Natural sources of ionizing radiation that form the natural radiative background are subdivided into external sources of extraterrestrial origin, cosmic radiation, external sources of terrestrial origin, i.e. radionuclides present in the Earth's crust, water, air, food, internal sources, i.e. radionuclides of natural origin contained in the human body. According to the potential danger of a possible entry of radioactive contamination into the biosphere, all sources can be conditionally divided into several groups. These include testing of nuclear weapons, enterprises for the extraction, processing, and production of fissile materials and artificial radioactive isotopes, and institutions, enterprises, and laboratories that use radioactive substances in the technology of production processes. No, and on this slide you can see as a unit for measuring natural radiation, 100 to 100 millibar a year. Quantitative characteristics of radioactivity. The study of the rate of radioactive decay of radionuclide nuclei made it possible to reveal a certain pattern. It has been established that not all atoms undergo decay at the same time, but for each time interval, a strictly constant fraction of the atoms of the radioactive isotope decays. This value is individual and constant for each radioactive element. It is called the decay constant. The decay constant shows the fraction of atoms that decay in the mass of a radioactive substance per unit time. Knowing the decay constant, one can calculate the time it takes for half of the isotope's atoms to decay, i.e. half-life. In radiation hygiene, it is accepted that the activity of a radioactive element becomes insignificant after 8 to 10 half-lives. The half-lives vary considerably for different isotopes. Isotopes with a half-life of a fraction of a second to several days are considered to be short-lived, and long-lived isotopes in which this period ranges from several months to billions of years. For example, for sodium, 15 hours, iodine, 131, 8 days, cobalt 60, 5.3 years, strontium 90, 29 years, iodine 129, 15 million years. The activity of a radioactive substance shows the rate of nuclear decay in an isotope per unit of time. Therefore, the activity of the radioactive substance increases with an increase in the mass of the isotope, as well as with a decrease in the atomic mass and half-life. For the unit of activity of a radioactive substance in the International System, international system, becquerel is taken. Such an activity at which one transformation of the nucleus occurs in the source per 1 second. However, historically, the first established unit of activity is Curie. It was first proposed by Marie Curie and named after Pierre and Marie Curie. Curie is a very large unit of activity. On this slide, you can see basic regularities of the effect of ionizing radiation on the human body. Among the main patterns are the following. All ionizing radiation leads to ionization of a biosubstratum of any composition, i.e. all organs, systems and tissues are, to one degree or another, subject to the destructive effect of ionizing radiation. There is a marked discrepancy between the low energy absorbed by the substratum dose and its pathogenic effect. Thus, it's known that 6,000 millisievert in acute exposure is a lethal dose. At the same time, the energy of this dose is only enough to hit 1 centimeter cube of biological tissue less than in 1 degree Celsius. This example indicates that the characteristics of the absorbed dose from the point of view of its energy alone is insufficient to understand the development of pathological process in the body. With a large damaging effect of high doses of ionizing radiation, an insignificant number of primary ionized molecules is observed. Thus, a dose of 6,000 millisievert ionizes only 0.001 of all molecules in the human body. An important aspect of the characteristics of the biological effect of ionizing radiation on the body is the lack of human senses capable to responding to the impact of this energy. A person is subjectively organoleptically unable to assess neither the time, nor the nature, nor the degree of exposure to ionizing radiation, which, taking into account the final pronounced damaging effect, makes this type of radiation extremely dangerous. And now we should discuss next question, the mechanism of development of radiation injuries of the body. Depending on the nature and localization of manifestations, distinguish several stages in the development of radiation injuries. Processes of primary changes under the action of ionizing radiation. In the process of studying biological lesions, scientists have proposed several theories explaining the characteristics of primary disorders with varying degrees of validity. One of the theories is the target theory. The essence of this theory is in the different sensitivity of various biomaterials and body structures to radiation. It is assumed that the cells of the body contain the most sensitive volumes, targets. If ionizing radiation hits such a target, the cell dies. If the radiation does not hit the target, then the cell remains alive. Another theory that tries to explain the nature of the development of radiation injuries is the theory of biologically active substances. The theory assumes that the number of minor primary injuries increases like an avalanche and leads to severe consequences as a result of the destruction of some cells and subcellular structures. For example, macrophages, lysosomes, to the release of biologically active substances, histamine-like substances, enzymes, into the intercellular space. Subsequent manifestations of autosensitization, autolysis, up to the death of the organism. At present, it is quite clear that these manifestations are only one of the stages in the development of radiobiological injuries. The most universal and generally accepted theory of the mechanism of development of primary lesions in biological tissues is the theory of indirect action, the theory of water radiolysis. According to this theory, about 50% of the absolute dose of ionizing radiation in a cell is in water. In this case, electrons are knocked out from water molecules with the formation of highly active toxic neutral radicals. The most highly active radicals, HO2, hydroperoxide, is a very strong oxidizing agent. It is formed when water is radiated in the presence of excess oxygen. And it may be formula H plus oxygen or O2 equal HO2. Thus, at this stage, changes occur at the level of physical chemical reactions with the formation of primary highly active radicals. H, hydrogen, connection oxygen with hydrogen, hydroperoxide and peroxide, which are not characteristic of the body and are very toxic. They give rise to chain reactions and secondary radical processes. The stage of biochemical transformations in the cell begins, and biological substrata enter into reactions. Proteins, carbohydrates, lipids undergo changes. Studies have shown that one of the very first disorders is damage to the synthesis of ATP, which in turn leads to a change in carbohydrate metabolism and tissue respiration. Simple sugars are oxidized and turned into toxic compounds, organic acids, formaldehyde. There is a violation of the properties of polysaccharides, so the mucopolysaccharide hyaluronic acid reduces its viscosity. Heparin loses its anticoagulant properties. No, and maybe direct action, because water radiolysis is indirect mechanism, and maybe direct mechanism which caused by damage of cellular nuclei. From the above, it can be concluded that due to the different level of organization, activity of metabolic processes, growth and division rates, the degree of radiosensitivity of cells is different. And here we say about law of Bergonier-Tribandot. According to this law, cells are more sensitive to radiation if reproduce more rapidly. Mitosis is more prolonged and less differentiated. And all these groups of critical organs may be distinguished on three groups. First group, the most sensitive to ionizing radiation, red bone marrow, sexual glands, small bowel epithelium. Second group, moderately sensitive tissue to ionizing radiation, internal organs. And third group, minimally sensitive tissues to ionizing radiation, skin, bones, cartilages, muscles, nervous tissue. The cells of the nervous, bone, and cartilaginous tissues are considered the least radioactive and resistant to the action of radiation. The most sensitive and radioactively affected are cells of hematopoietic and lymphatic system, as well as cells of the gonads. When exposed to ionizing radiation, not only structural disorders of cells and tissues and organs manifested by somatic determinant changes in the body, but also genetic rearrangements are of paramount importance. There are primarily gene or point mutations, a violation of the molecular structure of genes, and chromosomal aberrations, structural and numerical chromosome abnormalities. In radiobiology, the concept of relative biological effectiveness is introduced, which takes into account the effect of the biological action of various radiation under certain conditions. Relative biological effectiveness is defined as the ratio of the dose of X-ray or gamma radiation to the dose of any other type of ionizing radiation that causes the same effect. In this case, the relative biological effectiveness of X-ray and gamma radiation is taken as 1. The effect of ionizing radiation on a person. The biological effects of ionizing radiation can be considered from three positions. They may be determinant and stochastic, somatic and hereditary, acute and distant. Determinant effects are manifestations that are characterized by the presence of a threshold dose of radiation exposure and the severity of the injury in a particular person increases depending on the increase in the radiation dose. Examples of such manifestation are acute and chronic sickness, radiation burns, radiation cataracts, clinically recorded hematopoietic disorders, sexual sterility. Stochastic effects are manifestations that do not have a dose threshold. It is believed that any small dose of radiation can cause changes in the body of any severity, up to and including death. At the same time, large doses do not lead to an increase in the severity of the disease, but lead to an increase in the statistical probability of the frequency of lesions in the population. These disorders are caused by genetic changes and appear as long-term effects. Such manifestations include cancer, leukemia, and hereditary disorders in offspring. Somatic effects are effects that are manifested by the subject himself. For example, determinant somatic effects, radiation sickness, cataracts, clinically registered hematopoietic disorders, sexual sterility, as well as oncological diseases, stochastic somatic effect, leukemia. Hereditary manifestations include all violations in offspring caused by the impact of ionizing radiation on previous generation. Acute should include the effects that appear within a few hours or days after an acute exposure to a dose of ionizing radiation. In this case, it is generally accepted that the effect of the factor is acute either once or fractionally for no more than 4 days. There are such manifestations as acute radiation sickness and radiation burns. Long-term effects should be considered such somatic pathological manifestations as chronic radiation sickness, radiation cataract, clinically registered hematopoietic disorders, sexual sterility, as well as stochastic effects in the form of carcinogenesis, leukemia, and hereditary disorders. Determinant effects include somatic impairment only. They develop at the level of the whole organism and are associated with the coordinating activity of the central nervous system, which quickly reacts to the effects of radiation, mobilizes a complex of organs and systems, and initiates protective functions. The probable mechanism of this process can be represented as follows. The effect of ionizing radiation on the body turns on the central nervous system, which in turn triggers compensatory mechanisms, for example, humoral ones, which leads to compensation of pathological processes in the body as a whole. The limit of the possibilities of compensatory processes apparently explains the presence of a threshold in determinant manifestations. Exceeding this threshold leads to breakage of the compensatory mechanisms. All types of metabolic processes are violated. Protein, including enzymatic, nucleoprotein, carbohydrate, violation of the oxidative phosphorylation system, lipid. Of particular importance is not so much the depth of the lethal processes as the discoordination of the types of metabolism and body function due to the violation of the coordinating role of the central nervous system. The features and severity of the effects of radiation depends on 3 types of factors. From the characteristics of the organism, which are determined by sex, age, and individual characteristics, as well as the sensitivity of the organs exposed to radiation. Thus, it is known that ovae are more sensitive than spermatozoa, and the sensitivity of children and the elderly is higher than that of an adult organism. The former is due to the high mitotic activity of cells, and the latter is due to the violation of the processes of reparation and compensation. It was also established that the individual sensitivity of the organism is determined to a certain extent by the state of the central nervous system and its coordinating function, the level of human health, the functional state of the endocrine system. In addition, various organs and tissues, due to the peculiarities of metabolism, selectively deposit certain radioactive substances, and therefore are the most radioaffectable. The thyroid gland accumulates radioactive iodine, bone tissue, radium and strontium. The lymphatic system, isotopes of gold. Second feature, the strength of the impact is determined by the type and nature of the ionizing radiation. The higher the penetrating ability and ionization activity, as well as the greater the dose and radiation energy, the more pronounced the effect of radiation. And finally, the effect of exposure to radiation may depend on some factors and conditions: heavy physical exertion, high environment temperature, the simultaneous influence of chemical factors, etc. Now we should make break 10 minutes. Целикоксида, а еще какие не знаю, похожие. Целебрекс, целебрекс. Ну, в аптеке надо что спрашивать? Целебрекс. А еще А еще есть Делакса, да, я покупала. Ну что, ты вовремя вышел? А, угу. А ты утром заехал. Платил. Платил. Это сколько будет? По случаю рождения. Вот. Я не знаю, что. Конечно. Я же не так, что вперед. А потом его отпустить. Let's continue. Now we should discuss principles of hygienic standardization of ionizing radiation. The main tasks of providing radiation safety and the fundamental basis of radiation hygiene are preventing the manifestation of any deterministic effects by keeping radiation doses below appropriate thresholds, using all measures and implementing appropriate measures in order to minimize the likelihood of stochastic effects, taking into account social and economic conditions. And now we should discuss units which are used in radiation. We said about units of radioactivity is Becquerel and Curie. And now we should discuss other units. The nature of radiation damage to biological objects, including humans, when exposed to ionizing radiation, primarily depends on the absorbed energy. In this regard, such concept as absorbed dose is introduced. The absorbed dose is the amount of ionizing radiation energy transferred to the substance. The international system units of absorbed dose are gray. The off-system unit of absorbed dose is rad. 1 gray equal 100 rad. However, historically, the first empirically proposed dose characterizing only X-ray and gamma radiation was the exposition dose. Exposition dose is a quantitative characteristic of X-ray and gamma radiation in terms of their ionizing effect, expressed by an electric charge of the same sign formed per unit volume of air under conditions of electronic equilibrium. In the international system, the unit is a coulomb per kilogram. The exposition dose of X-ray and gamma radiation, which creates ions in 1 kilogram of dry air that carry a charge of 1 coulomb of each sign. The non-systemic unit is the X-ray or Röntgen. Such an exposure dose of X-ray and gamma radiation, which creates ions in 1 centimeter cube of dry air that carry a charge of 1 electrostatic unit of each sign. The equivalent dose is the absorbed dose in an organ or tissue multiplied by the appropriate coefficient for a given type of radiation. The international system unit of absorbed equivalent dose is called Sievert. The non-systemic unit of the equivalent dose is Ber. Ber is abbreviation, biological effect of rad. And in medicine, more often we use these units of equivalent dose. In international system, Sievert, in non-systemic unit, Ber. But traditionally in Russia and Ukraine, we use BER, but in other countries, and now we also use unit Sievert. An important characteristic of the effect of ionizing radiation on a person is the dose rate. That is a dose per unit of time. For example, you can see on this slide unit of exposition dose rate. It's Röntgen per hour or milliröntgen per minute, microröntgen per second. To ensure radiation safety during normal operation of radiation sources, it is necessary to observe the following basic principles. Not exceeding the permissible limit of individual doses of exposure of citizens from all sources of ionizing radiation. Prohibition of all types of activities involving the use of sources of ionizing radiation in which the benefits obtained for humans and society do not exceed the risk of possible harm caused by radiation additional to the natural radiation background. Maintaining at the lowest possible level, taking into account economic and social factors of individual radiation doses and the number of exposed persons when using any source of ionizing radiation. Hygienic standards are differentiated for different groups of exposed persons. There are the following categories and groups of people exposed to radiation. Category A, personnel, persons working with man-made sources. Group B, persons who are under the working conditions in the sphere of influence of man-made sources. Category whole population, including personnel outside the scope and conditions of their production activities. On this slide you can see for personnel category A, maximum permissible dose and concept. You can see first of all concept of MPD. It's a dose that must not cause any pathological changes in the staff during the period of work. And maximum permissible dose for personnel category A is 5 beer per year, or 50 millisievert, or 100 millibear per week. For category B, this level 0.5 BER per year, or 5 millisievert, and for population 1 millisievert. In accordance with the goal of medical exposure of the population, the principles of control and limitation of radiation effects in medicine are based on obtaining the necessary and useful diagnostic information or therapeutic effect at the lowest possible levels of exposure. When carrying out preventive medical X-ray examinations of practically healthy persons, the annual effective radiation dose of these persons should not exceed 1 millisievert. Providing radiation safety. Radiation monitoring should include periodic monitoring of the exposure dose rate at workplaces, in adjacent premises, in the territory and in the sanitary protection zone of the facility. Monitoring the protective properties of stationary fences. Monitoring the protective properties of non-stationary and personal protective equipment. Dosimetric control of staff. Individual dosimetric control of persons belonging to category B, periodically participating in special X-ray examinations. For example, surgeons, anesthesiologists, to limit radiation exposure. Control of radiation exposure of patients. On this slide, you can see effective doses of patients' irradiation in X-ray examination. For example, chest X-ray gives 0.15 millisievert. Chest X-ray scopy 1.8 millisievert, sometimes more than usual chest X-ray. Chest fluorography 0.8 millisievert, urography 0.6 millisievert, bowel X-ray scopy 2.6 millisievert, very high level. Kiss X-ray low level 0.03, CT of the chest 7 millisievert, mammography 0.7 millisievert. We can see CT, computer tomography, gives very low, very high level of irradiation. Ensuring radiation safety as a rule requires a whole range of diverse protective measures depending on the specific conditions of work with sources of ionizing radiation and first of all on the type of radiation source. Sources of radiation are closed and open. Closed are any sources of ionizing radiation which exclude the entry of radioactive substances into the environment. It can be seen from this definition that when working with closed radiation sources, personnel can only be exposed to external irradiation. Therefore, all protective measures in this case are carried out taking this circumstance into account. X-ray, for example, X-ray examination, it's example of closed sources. Gamma irradiation devices, also example of closed sources, because only rays enter environment, any corpuscular. Sources of ionizing radiation are called open when using which it is possible to get radioactive substances into the environment. In this case, there may be not only external but also additional internal exposure of personnel. This can happen when radioactive isotopes enter the working environment in the form of gases, aerosols, and also in the form of liquid and solid radioactive waste. If we have combination of particles and rays, such source will also belong to open sources. If only X or gamma rays, closed. If alpha particles, beta, it's open sources of radiation. Basic principle of providing radiation safety. Reducing the energy of sources to minimum value. It's protection by quantity or protection by dose. I.e., at observation of maximum permissible dose, we protect person against radiation. Reduction of the time of work resources, time protection. In our slide, it's 0.3 protection by time. Restriction of work time with ionizing radiation. Increasing the distance from the sources to the working ones. Protection by distance. Shielding of radiation sources with materials that absorb ionizing radiation. Protection by screens or by shielding. The main principles of protection when working with open sources of ionizing radiation include these four main principles. The use of the principles of protection applied when working with radiation sources in a closed form, plus additionally one should provide pressurization of sources automatization of work, special systems of ventilation and sewerage, special planning premises, isolation, separated room for work, rest and patients using non-absorbable materials, special premises for storage of radioactive substances and radioactive wastes, and usage of individual protective measures, masks, gloves, suits, dosimeters. But in this picture you can see such individual protective measures. And periodic radiometric control of radio pollution of the air, water and solid materials. It is carried out by special devices, radiometers. Workers must wear biodosimeters which show accumulated dose of radiation. On this picture you can see kind of such individual dosimeters. They are like on usual pencil. And we can put such a dosimeter in the lab coat, and periodically data from these dosimeters are taken for registration, received dose by specialists. Sources of radioactive contamination of the biosphere. With the beginning of the widespread testing of nuclear weapons, global pollution of the biosphere with artificial radionuclides arose. Added to this are local, regional, and global pollution caused by wastes from nuclear power plants and the use of sources of ionizing radiation for scientific purposes in medicine and in the national economy. Significant environmental pollution can occur as a result of accidents at nuclear power plants. According to the potential danger of a possible entry of radioactive contamination into the biosphere, all sources can be conditionally divided into several groups. These include testing of nuclear weapons, enterprises for the extraction, processing, and production of fissile materials and artificial radioactive isotopes, institutions, enterprises, and laboratories that use radioactive substances in the technology of production processes. Radiological departments of the Sanitary Epidemiological Station carry out radiation monitoring, both in case of emergency contamination with radionuclides and during periodic investigations of the radioactive substance content in environmental objects, food products and drinking water, soil, vegetation, water of reservoirs, and food raw materials. Now we should discuss question due to methods of radioactive waste neutralization. Methods that are used in the processing of waste can be divided into two categories. The first one is the exposition in time, storing waste until all or almost all of the radioactive substances disintegrate. Usually, if there is a mixture of radioactive elements in the waste, the maximum exposure time is determined by the isotope having the longest half-life, and the period itself is assumed to be 10 half-lives. For example, for iodine 131, 82 days. The second category is the dilution of waste to negligible levels of activity. Those do not pose a danger to public health. Removal of radioactive waste. The radioactive waste disposal facility is an enterprise that provides centralized collection, disposal, transportation, and burial of radioactive waste. Such special facilities are arranged for the burial of waste of a large industrial area, city, or region. In cities where work is being done with radioactive substances, liquid and solid radioactive waste is usually collected in special receivers containers. Dosimetrists of the receiving service of the disposal point check the pressurization and strength of the packages, the intensity of gamma radiation, and neutron radiation from them, contamination by radioactive substances. The radiation dose rate from a container with radioactive waste should not exceed 10 millibar per hour and a distance of 1 meter. Nutrition in intensive radioactive burden. This question was actual, became actual after accident on Chernobyl nuclear power station. Up to 94% of radionuclides come from food, 5% from water, and 1% from air. With increased radioactive burden, the following is recommended. Increased amount of proteins in the diet, especially sulfur-containing ones. Sulfur-containing proteins usually food of animal origin, proteins of animal origin. Strontium 137 is removed from the bones, internal organs, and blood. Increased amount of vegetable fat and animal fat must be only 10%. From the carbohydrates, increased cellulose and pectin substances. Among vitamins, antioxidant vitamins A, E, C, which remove free radicals, and 2-3 times requirement usage of such vitamins must be 2-3 times more than the daily requirement. Mineral substances, calcium, prevent the accumulation of strontium in the bones. Sources of calcium: dairy products, legumes, meat. Selenium contained in bananas and plums. And now we should discuss some questions due to ecological and medical consequences of Chernobyl accident. Radiation accident, a loss of control of sources of ionizing radiation caused by equipment malfunction, improper actions of workers, personnel, natural disasters, or other reasons that led to exposure of people above the standards or radioactive contamination of the environment. The accident in the Chernobyl nuclear power plant occurred on April 26, 1986. The thermal explosion at the power unit led to the release into the atmosphere of 50 tons of evaporated nuclear fuel, creating in the surrounding atmosphere a huge reservoir of long-lived radionuclides: uranium, plutonium, cesium, strontium. In the initial period of the accident, the dominant dose-forming factor was internal exposure to iodine 131 short-lived radionuclides with a half-life of 8 days, concentrating mainly in the thyroid. Then external and internal exposure to cesium-137 radionuclides with a half-life of 33 years, which are evenly distributed in the muscles when they are ingested with water and local food, milk, meat, potatoes, mushrooms, berries become the leading ones. After the passage of the cloud resulting from the accident at the reactor, the gamma radiation dose rates causing external exposure of people correlate with the amount of precipitation. Thus, the area of Kiev after the Chernobyl accident at the beginning of May 1986, dose rate levels reached 500-800 microRöntgen per hour. By the end of 1987, the gamma background increased by 10 times. Radioactive contamination of soil, vegetation, food, water bodies, various objects in the territory was caused by radionuclides with an average half-life strontium 89, barium 140, ruthenium 106, cerium 141, 144, zirconium 95, and then long-lived cesium radionuclides and cesium 137, 134, strontium 90. On these pictures you can see different monstrosity. Different types of monstrosity of babies. According to the Association of Chernobyl Doctors, among those affected by the Chernobyl disaster, the incidence and prevalence of the main classes of diseases, especially the nervous system and mental disorders, disorders of the endocrine, digestive, respiratory, and cardiovascular systems, as well as oncological pathology, continue to increase. The most critical contingents to the effect of ionizing radiation are persons who have undergone acute radiation sickness, participants in the liquidation of the consequences of the Chernobyl accident in 1986, 1987, including for a long time, 5 years and or more, working in the Chernobyl exclusion zone. Children, including irradiated intrauterine. According to epidemiological studies in the affected countries, there is an increase in the incidence of thyroid cancer among liquidators of the accident, evacuated population, and residents of radioactively contaminated areas. Due to increase of kids' age, the peak of thyroid cancer has moved from the early childhood age group to the adolescent and young age groups. An increase in the frequency of leukemia is observed in liquidators irradiated in the first days after the accident, and almost fourfold increase in the prevalence of mental disorders among staff working from 1986-1987 was noted. Lecture is finished. Thank you for attention.